Well, let us go to the next part of this tutorial to complete the analysis of the slope. And I have again started with geometry module. And in the geometry module, since my mesh is on this two faces, and these two faces collectively makes this partition 1, so now I must create the groups on this geometry first. Earlier I had created the groups on lines and two faces, but since my mesh geometry is basically partition 1 and submesh geometry is the inner part which is part of the partition 1, therefore I must create the geometry, groups in geometry in the partition 1 itself. So I had deleted the earlier created groups, and now I will redo the grouping based on the geometry that is partition 1. So I have selected partition 1. Now new entity group, create group. First let me create the point groups. So say toe point is the name of the point is the name of the group, and I'll select this one, then add, apply, then I'll select the top point, so top point, and I'll select this point, add, apply, then I need to select the line for support. Okay, so what I'll do is next I'll create the group of lines. This I'll call support, and I'll select on this line, then add, then this line, then add, and then this line, and add, apply and close. So support we have made, and then I need to create the whole slope face. So once again group, create group. Now this will be of type face. I should select partition before doing that. So partition, then new entity group, create group. It's kind of face, then this is I'll call slope face, and then I'll select this, then add, and then this, then add, apply and close. Okay, so let me save it. Now let us go to the mesh module once again. Mesh module, this mesh is already there. So in mesh 1 now I will create group from geometry. So from mesh menu I'll select create groups from geometry. So I'll select these 2 points, all these things, and nodes also from here. So I'll create nodes and elements from everything. In fact, this toe point and top point I can remove from here. I can remove from here if I want, but there is no harm, I think, if I keep it in the elements also. So apply and close. So in my mesh now I have groups of nodes and groups of edges and groups of faces. Okay, so let me save it now. So now my mesh is ready for analysis, and therefore sorry, I'll go to the module Aster-Study. So here I have this case 1, so let me add a stage. Now once I have this stage, these are my different menus: mesh, model, definition, material, functions and lists, and there are 2 more menus which I can see from here: fracture and fatigue and output. So I can select from these menu items, or I can also select the menu items from these commands. So it gives all these menu buttons as a drop down list here. So anywhere I can go to select this. Now my first job is to read the mesh. Well, I think I have again missed one stage in the mesh module. So in the mesh, what I can do is I can select this mesh one, and I can export it to a MED file after the mesh is finalized. I should not export before finalizing, because whatever change I am doing in geometry or mesh, automatically these things are updated if it is in the HDF file. But I should also save the mesh in a separate file for further studies. If I want to apply strength reduction method in the same mesh, then I will not recreate the mesh, I will use the same mesh. In that case, it will be easier for me to load the mesh from a mesh file. So what I will do is I will right click on the mesh and I will select the export menu, and MED file is the default native format for Salome-Meca. So let me select MED file. There is some error message. There are duplicated group names in mesh 1. You can cancel exporting and rename them. Okay, let us see what has happened. Submesh, then groups of nodes, toe point, top point, support, slope face, and groups of edges, support, groups of face. Okay, this has been doubled somehow, so let me remove these 2 from here by deleting it. Yes. So now groups of node is toe point, top point, support and slope face, and groups of line is support, and group of face is support face. Now I think I can export. Let me save the HDF file and then export it, MED file. So now nothing has come. So this is my mesh 1. Let me save it in a file name. The file name is mesh 1. Okay, let me save it. So in my this thing I have got this MED file containing the mesh. Okay, now once I have done that, let me go to Aster-Study once again, then stage, then first I should read the mesh. So read the mesh. Now I can either read from the HDF file directly, or I can read from this mesh file location. If I click here, this is my MED file. It has automatically selected, so I'll click open. So this has come, then I'll call it. Okay, so this has been the command has been generated. Now if I want to edit this command, I'll select here and right click edit. Now this mesh file format I think I should add at least, and therefore I have checked this one, made file format. Okay. So accordingly this command has been updated. Now after reading the mesh, in this case I don't need any modification of the mesh, so let it be like this. Then I can go to model definition. For that I will assign the finite elements. The name of the model is model, then mesh is that mesh file. Then here I will write finite elements one item. Let me edit everywhere, and the phenomenon is mechanical, and what kind of modelization it is. It should be D-plan. So let me select D-plan from the menu. D-plan, that means it is plane strain analysis I am going to do. So there is my D-plan. Then okay, so the corresponding Code-Aster command has been generated automatically. So this is the advantage of having Aster-Study. Now then my job is this is done. Then I should define my material first. So go to material menu and define a material. Now in this definition I'll call the material as soil, because this is a soil I know. Then linear isotropic values I should give. So the value of E for the soil is 20 megapascal. So 20 exponential 5 in Pascal. Then Poisson's ratio is 0.2. So this is my elastic part definition. Okay. Then I should go to the Mohr-Coulomb material here. So let me find Mohr-Coulomb. I can search Mohr-Coulomb, it has come. So let me edit the Mohr-Coulomb. So it needs 3 parameters: angle of internal friction phi, then angle of dilation, and the cohesion. And so my phi value is 35 degree, angle of dilation is 15 degree, and cohesion is given as 10.5 kilopascal. So 10.5 exponential 3 in Pascal. So okay. Now I should also add the self weight. So let me edit this command. So linear isotropic, let me add density here. Density will be 2200 kg per meter cube, because my filled bulk density of this soil is 22 kilonewton per meter cube. So that makes the mass density as 2200 kg per meter cube. So okay. So this is my material, and then I need to assign the material. Assign a material. So field mat, mesh is layer measures, then model is the model, then material assignment. Let me edit. Material is everywhere. Yes, material is which one? The soil. Okay. So everywhere I have assigned the soil material. Okay. So I have assigned the material. Now I need to use the functions and lists, and for that purpose I will use first the multiplying function, and I will also use the list of instance at which I need to carry out my analysis. Okay, you know that in nonlinear analysis loading has to be parameterized by time. For that purpose I need some multiplier functions, so functions and lists. Define function. Let me call this a ramp function. Then I will have coordinates, edit. I can have the values of coordinates. In 0 instant my function value is 0, and then I can add one more line. Then maybe at instant say 20 I have the value of multiplier as 1. So this is my and the parameter is time. That means it is the variation is with respect to time. So time, parameter is time. Okay, so ramp is défi fonction, numpera is inst, values are 0 at 0 and 1 at 20. So my multiplier function is defined. Then let me have another list, that is list of time instance at which I should carry out my computation. So I will create a list of reals by the function defi_list real. So values I will have, no, I will not have values. Let me call debut is 0.0, and what are my interval is up to say about 25% of the load. I want to use elastic behavior of the soil. So since my total load is applied at time instant 20, so 25% of 20 is 5, so up to 5 I will use a higher number of interval, higher value of interval. So I will give pass as 1. So okay, and then I should add one more. So edit, then up to 20 I will go with a step of say maybe 0.25. let me see, 0.25. So up to 20 I will go by 0.25. Let me define it like this. So this is my list of reals. defi_list real, debut is 10, interval up to 5 is 1, and up to 20 the interval is 0.25 from 5 onwards. Okay, so this is my list of the time instance, and then I can have a defi_list inst. What is the list of time? So name is times, and which time step list I have already defined that in the list R. So I have selected this, let me check whether this, what is this, let me check once. Yes, so if I do not arrive at the convergence within those given time lists, then I can cut down my time step and subtipass mini. I'll make it 1e minus 0.6. I think this is okay. So okay. So this says me that if I don't get the convergence, then I should cut down the step, and the minimum pass mini should be 10 to the power minus 6. So let me edit it. It is not subtip pass mini. Subtip pass. I think let me put the default value. Okay, let me put the default value. So I have defined my functions and lists. Now I can go for assigning the mechanical load. Okay, assign mechanical load. Now I have two things. One is the boundary condition, let me call it BC, and enforced UF I'll have dx equal to 0 and dy equal to 0 on the support. So group of nodes, support, I'll select support. So this is the line where I am applying these boundary conditions. It has been made yellow now, so I'll call okay, this is my boundary condition. Okay, and then I'll assign a new boundary condition, new load, assign mechanical load. This I'll call it self weight, and then it is gravitational. Let me edit. Directions are cancel. Direction is zero in x direction, in the downward direction in y, and this is 0, and gravitational constant is 9.81 meter per second square. Okay, so only self load is there. So both BC and self weight I have got it. Let me save it. Then pre-analysis, I don't need anything here in this case. Then go to analysis. Now we'll go for stat non-line operator. Where is there? Stat non-line operator, yes. Now model is this, material is this, loads, I have two items here. Let us select the loads. So for first load, boundary condition, no multiplier function is there. Okay, then one more item I should have, that is the self weight. So for the self weight, the multiplier function is ramp. Okay, then time stepping is time list, that is times. Okay, so okay, and let me check if there is something more is needed. No, it is not needed. Then I will have to use the method Newton, and then this I'll call code. This is the line search method, arc chord method, or I can otherwise use code. Okay, then on convergence I have to have Resi-Globe max C. I'll keep it as 1e minus 2 because this means the error of 0.1 Newton, which is a very, very small error. Default value is 10 to the power minus 6, but I do not need that much accuracy. So Resi-Global max C is 10 to the power minus 1, and Resi-Globe relative, of course, I should have 1 exponential minus 5. Okay, then Iter-Globe max C, I will use at least 10,000. Let me check. Rate is yes, and that means it will stop if convergence is not achieved. Okay, and then I should modify the Newton's method by I will use the elastic matrix because it is a highly nonlinear material. So okay, well, in the beginning I want to have, for the first few things, I want to have for the first 5 steps, you see my list for real, I had up to 5, the pass was 1. So for that purpose, let me use one result, this result for elastic case. So let me edit it. I'll call it res 01, and in the time stepping I'll end time step as 5.0. okay, so up to, that means time step 5, we will use comportment as linear, okay, then material field, fine, time stepping is okay. Then this comportment I'll have elastic relation here, elastic. Okay, so it is okay. Okay, so up to final instant of 5, it will use elastic material. Comportment relation is elastic, and in the Newtonian method it will use the initial tangent matrix, that is elastic matrix, for this. Okay, so this is my first nonlinear analysis. Then I will add one more nonlinear analysis where actual analysis will be once again nonlinear this time. So this is my race 02, say model is 10, loads I have 2 loads, one is BC without any ramp function. Okay, then this is self weight with multiplier function ramp. Okay, then time stepping the same time list, but now this etat init, I should have this etat init, that means initial condition, and comportment. My comportment is not elastic, it is Mohr-Coulomb this time. Mohr-Coulomb, and then deformation is small, of course. Then okay, and then initial conditions I should add. What is my initial condition? Initial condition is race 1. That means you start analyzing with Mohr-Coulomb result from the 5th time instant onwards. Okay, and the time step list is, I should have DPL, I should have sigma as well. No, this is not there. Then numerology, so this is okay, I think. Then method is again Newton, and rich line is again Code-Aster. I'll use Code-Aster. Okay, okay, and then convergence, I'll use again the same thing. Resi global maxi as 1e minus 02 and Resi global relative as 1e minus 05. Okay, then hydra globe maxi will be again 10,000. Arret is yes. Okay, and then the Newtonian method I will modify by using elastic matrix. So matrix will be elastic once again. Okay, okay, I think everything is okay now. Result 2 starts from a user is Mohr-Coulomb relation, then 10,000 in one time step, maximum number of iterations. Resi globe max is 0.01 and Resi globe relative is minus 10 to the power minus 5. The loads are BC and self weight with Fonck multiplier ramp. Then the times So okay, so this is my analysis. Then let me post process. So first is calc CHOM, that means calculate the these things, stresses. I will use this result. I'll call it again res02. I must use the same name. Then model is model, material is material, the out order yes. Then I will write contract, that is the stresses. I will have 4 types of stresses I will list. So sigma alga, then sigma at nodes, then CF CEQ no, these are not there. Then deformations, that means the strains. I'll write FC alga, and I'll also add FC at the nodes. Okay, and I should edit it. Sorry, I should edit this by selecting the criteria. I should add 2 criteria, that is equivalent sigma 1 minus stress on element gauss and element nodes. Not element nodes, actual nodes. Okay, so this is the results. Then I must set the output results. So output, set output results, that is mprezu. So first I will save the results in a new file. So file name is, I will call it res02.rmed. in the same place. Format is mad. Then results is mesh. Then which result I want? I want this one, raised to calc CHOM, and okay, then okay. And I would also like to write in the tabular form the deformations of the toe point and the top point. So I should have one more output command, output, set output results. Now I will have, instead of med, I will use result format. Now this result file location is slightly different. So res02.say out, it's a text file. So save, and then what I want to have, I want to have mesh and result to state non-line. That means only the displacements I would like to see. And where do I want to which thing I want to write group of node. I'll have to select manually. Group of node was to point. Okay, comma top point. Also, I do not know why it is not coming. Format R is this. Okay, then group of node is okay. Then I want the time space. Okay, then model is model, and let me see if this is okay. Data files I have raised to the out and are made okay. I think things are okay now. This is resulted group and auto point and top point, mesh result 2. Okay, so I think this is okay, and this is also impressive. Okay, so let me save it once again. Now I think I can run the analysis. For that, let us go to history view. This is my stage 1. Run. I'll allot at least 4 GB of RAM, so 4000 MB, and time I will give quite a few hours, maybe 6 hours. Run. Let me see what happens. For some time, if it runs okay, then it should not stop. It will take quite a bit of time. So I think now we can pause the video and see what happens. Hello. So my analysis is over. We have got a green circle, so the analysis is successful. So it has said that calculation process started. Then it has copied the results in those armed and out files, and it has said that calculation succeeded with state success plus warning. Calculation process finished. So this completes my analysis process. That's very good. And in the next part, we will see how to post-process the results using Paravis. So for that, let me go to case view again, and let me go to data file. Then this is my med file where result has been written, so I can open it in Paravis. Takes a little bit time. Let us see what happens. Close. So properties, information, fine. So it gives me raise FC, raise DPL, everything. So let me go to information, properties. I can see these things here, and then let me see surface with edges. So let me see what is the DPL. There's my deformation in magnitude. Okay, and if I want to see dy, then what is the maximum value of the deformation? Minus 1.95 meter. It is a huge deformation. Maximum 1.95 meter. So let me edit this coloring scheme. Let me go to, I like this one because it shows the ranges very clearly. So we have this minus 1.952 in meters. It's a huge deformation. So let me apply the warp by vector filter. Filters common. Warp by vector is not has not been activated. Information. Is my information and properties. Magnitude. This is my magnitude. So 1.956. It's a very huge deformation. I should be able to see it if I apply filters to it. Common, warp by vector. I don't know why it is not working. Let me see why it is not working. Okay, generate vectors, apply. I think now I'll be able to apply this filter. Common, warp by vector. Now this is my deformation. There's my deformation. I'll see it with edges, and the earlier one I will see it only with surface. So this is the deformation. The slope has undergone. Okay. Apply. And here what I'll do, I'll use a single color for this property. properties. I'll use display. I'll use maybe black and white. Let me apply. No. It has been applied in the whole thing. Let me use blue to red rainbow. And this is surface. Okay, so this is my kind of deformation we have got, and this is my magnitude. But if I select dz then dy, then this is my kind of deformation. It's a very huge deformation we have got, 1.95 meter. So, but things have not failed yet. Now let me see what is the strain distribution. So let me close this. Now I will see the strain distribution. Let me see the strain distribution. For that I will apply another filter, that is mechanics filter, alga fill to the surface, let me study this FC alga thing. So let me see PXY1 surface with edges. So the maximum strain is minus in the blue region, so this is my region. Let me use a different coloring scheme. So alga properties, let me use this blot one, apply. So this is the, or let me apply some another scheme, maybe rainbow, apply. So we have maximum strain, shear strain somewhere here, and that value is 2 to the power minus 2 to the power this thing, and here also we have shear strain. Let us see what is EPYY. This is a small one, somewhere here. This is the value. So then FC alga vector, let us see, EPXX, EPYY, EPZZ should be 0, EPZZ should be 0, yes, because it is plane strain obviously. Then let us see the stress distribution. See the stress distribution here. This is my magnitude. This is my shear stress distribution, which is quite high in this zone. Let me apply. And let me change the representation. Say red to blue rainbow, apply. So alga fill to the surface, sigma alga, shear stress is this direction here, clockwise, and here it is. So this is where we have got certain failure kind of thing. And let me see, what is this value? Von Mises stress. Von Mises stress is 6.3 into 10 to the power 03. And triaxial stress is this one, minus 1.3 Pascal, and von Mises stress is in this zone 6.3 kilopascal around. So it is the solution. So that's how we can we can visualize the stresses. With this we finish this tutorial. Hope all of you enjoyed it. Thank you for watching. Thank you.